When Kawasaki CEO Yasuhiko Hashimoto stood before the crowd at the Global Technology Showcase, the energy in the hall shifted dramatically. Months of anticipation had built toward this moment. Every manufacturer in the two-wheeled realm had been watching Kawasaki for hints of what might come next. A hush settled when the CEO walked onto the stage, and powerful lights illuminated a sleek platform that held the new creation. Attention focused on every line of that engine, and on every indication of its potential performance. Observers had expected incremental gains, but instead witnessed a proposition that defied conventional assumptions. Engineers who had studied thermal efficiency and power delivery for decades found themselves recalculating possibilities. That single presentation would ripple through boardrooms, research labs, and racetracks around the world. An eruption of excitement and disbelief flowed outward from that platform and would soon transform the course of motorcycle development. Before we start, hit the like and subscribe buttons for more exclusive news. The gathering included journalists, writers, engineers, and executives who had traveled from every continent in pursuit of insight into Kawasaki design philosophy. Some had dared to hope for a radical step forward, but few had anticipated the scale of the breakthrough revealed. Discussion had centered on turbocharging lightweight materials and electronic integration. Yet what emerged from the unveiled power unit surpassed all speculation. That machine combined innovative combustion techniques with an advanced cooling system and a compact architecture that redefined expectations of size, weight, and output. Observers noted that the new unit produced power densities previously unreachable without heavy forced induction or exotic components. Balance and responsiveness held promise for both street and track machines. The design set a new benchmark that others would scramble to meet. Yasuhiko Hashimoto had spent years refining his vision of high performance that remained accessible and reliable. He had guided Kawasaki through phases of experimentation with variable valve timing and lean burn combustion systems. Under his direction, the design teams embraced computational fluid dynamics and additive manufacturing processes to push boundaries. This time, however, the decision to revisit fundamentals of thermodynamics and combustion chamber design resulted in a leap that eclipsed earlier advances. The new approach optimized gas flow swirl compression ratio and ignition timing in a unified package. Control systems adjusted key parameters in real time based on feedback from sensors embedded deep within the engine. The holistic integration across hardware and software marked a departure from the modular upgrades that had characterized previous generations. Engineers in attendance studied technical drawings projected onto large screens as the unveiling progressed. They noted that the cylinder walls incorporated a novel ceramic composite lining that reduced friction and enhanced thermal resistance. Cooling passages followed a three-dimensional array that circulated coolant precisely where heat peaked under high RPM. The crankshaft featured a hollow structure that balanced rotational inertia and saved weight. High-strength steel connecting rods linked to forged aluminum pistons designed with cooling galleries that circulated oil to maintain temperature under demanding loads. Each element worked in concert to sustain operation at RPM ranges that had been deemed unsafe for production engines. Observers recognized that this creation would translate into extraordinary acceleration and sustained high-speed performance. Beyond the engine itself, the ceremony introduced a lightweight suspension system that complemented the power unit. That shock absorber assembly utilized a new damping fluid and a variable flow valving mechanism that responded instantly to changing terrain. It integrated directly with chassis sensors and steering angle feedback to provide adaptive damping. When riders encountered sudden corners or rough surfaces, the system stiffened or softened in milliseconds to maintain optimal tire contact and stability. Combined with the reduced, unsprung mass derived from lighter wheels and brakes, the result offered handling precision even at extreme lean angles. Designers stressed that this integration between engine and suspension represented a new era in machine synergy rather than isolated component improvements. The immediate reaction among competitors ranged from admiration to outright alarm. Rival manufacturers had allocated large budgets to research next-generation motorcycles, but few had ventured into the degree of integration displayed by Kawasaki. Some insiders admitted feeling blindsided by the timing and scope of the announcement. Board members of other brands began convening emergency strategy sessions to reassess development timelines. Suppliers of engine components and electronics initiated scans of patent databases and research papers to reverse engineer potential methods. The shockwaves extended even to aftermarket specialists who sensed that familiar tuning approaches might require complete reevaluation. The balance of power within the industry had shifted in the span of an hour. Racing teams affiliated with Kawasaki immediately penned plans to incorporate the new engine into prototype machines. Development writers lauded the prospect of achieving top speeds faster while maintaining traction and control. Test sessions scheduled on circuits from Motegi to Le Mans promised to calibrate the integrated suspension and engine control systems under extremes of temperature and high G-force. Engineers would map throttle response against track data and refine electronic power delivery curves to suit various racing classes. Rival teams began scrutinizing footage of the announcement to extract design cues. The emergence of a production-level unit with racing-caliber performance had blurred lines between factory machines and customer race bikes. The supply chain implications proved substantial. Kawasaki announced partnerships with specialized material providers for ceramic composites and advanced polymers needed for seals and gaskets capable of handling higher pressures and temperatures. Coolant suppliers reworked formulations to suit tighter cooling passages without risking corrosion or cavitation. Electronics manufacturers adapted microcontroller firmware to manage the complex control loops required by real-time engine and suspension data fusion. Assembly lines faced retooling to handle precise tolerances measured in microns. Staff training programs would accelerate to equip technicians with the skills required for system diagnostics and calibration. Those changes signaled a broader shift toward more sophisticated manufacturing in the motorcycling world. Dealers felt a surge of renewed interest from enthusiasts eager to reserve machines equipped with the new technology. Pre-orders soared as committed riders recognized the potential for setting new lap records and enjoying more refined street performance. Market analysts revised sales forecasts upward, predicting that Kawasaki would gain market share in high-performance divisions. The ripple carried through finance departments as investment firms adjusted valuations of Kawasaki stock in light of anticipated revenue growth. Brand perception took on a more futuristic aura as Kawasaki emerged as a leader in integrated machine engineering rather than simply a builder of robust engines and chassis. The announcement would likely elevate Kawasaki above its traditional rivals in brand strength. Enthusiasts debated at length on social forums regarding the merits of a high compression ratio engine that balanced power output and fuel economy. Technical blogs dissected patent filings and speculated on the potential horsepower and torque curves. The lack of performance figures during the event fueled further speculation and rumor. What mattered most, however, was the concept itself. The idea that a production motorcycle could deliver both impressive dyno numbers and real-world rideability challenged long-held industry assumptions. Most prior attempts sacrificed reliability for peak power or smoothness for performance. Kawasaki had reportedly managed to reconcile those elements into one cohesive product. Environmental considerations lay at the heart of the new design as well. Kawasaki highlighted that the optimized combustion process reduced unburned hydrocarbons and nitrogen oxide emissions without compromising throttle response. Achieving tighter control over the fuel-air mixture and exhaust gas recirculation allowed that engine to meet stringent emission standards in multiple markets. That approach offered a path for manufacturers to pursue performance goals while satisfying tightening regulations. Competitors facing the cost and complexity of separate clean engine initiatives recognized that the integrated solution from Kawasaki could raise the bar for compliance and performance simultaneously. The event underscored the way technological advancement and environmental responsibility could converge. Manufacturing facilities designated for the new engine line saw blueprints roll out immediately following the event. Assembly plants in Japan and abroad would install high-precision machining centers, coordinate measuring machines, and laser alignment systems. Skilled operators received instructions on new protocols for handling ceramic composites and managing waste streams responsibly. Quality control laboratories would expand testing capabilities to include high-speed vibration analysis, thermal imaging inspections, and endurance cycle rigs capable of replicating years of use in a matter of days. The level of sophistication required would likely spur other manufacturers to upgrade facilities to remain competitive, creating a wave of capital expenditure focused on advanced manufacturing. Aftermarket parts suppliers confronted both challenge and opportunity. On one hand, the complexity of that engine might limit traditional bolt-on enhancements. On the other hand, modular interface points favored by Kawasaki design philosophy could allow specialized tuners to develop bespoke control modules and suspension upgrade packages. Custom shops would need to adapt by hiring engineers capable of software development and sensor network integration. Tires and brake pad manufacturers saw a market for compounds optimized for the unique power delivery and handling characteristics of the new machines. Those changes would shift the aftermarket landscape toward integrated system upgrades rather than simple component swaps. The announcement also impacted talent acquisition strategies. Kawasaki had signaled that cutting-edge mechanical design and software integration were equally valued. Recruitment efforts would emphasize multidisciplinary engineers skilled in control theory materials, science and data analytics. Universities and research institutions noted the significance of the event and sought partnerships to develop curriculum aligned with the vision put forth by Kawasaki. That synergy between academia and industry would strengthen innovation pipelines for the entire sector. Competitors would follow suit, enhancing educational collaborations to attract promising students and researchers passionate about blending hardware and software in pursuit of performance. Global markets responded with varied enthusiasm. In Europe, dealers in alpine regions anticipated machines that could handle winding roads with unprecedented agility. In North America, power touring riders eyed the potential for long-distance comfort combined with track-oriented performance. In Asia, urban riders appreciated the promise of smaller, lighter power units offering nimble handling in dense traffic. Kawasaki planned to tailor model variants for each region with specific engine mappings and suspension settings. The event highlighted how a single technological core could yield diverse products for disparate markets, extending the reach of Kawasaki and reinforcing its position as a truly global innovator. Financial analysts examined how research and development expenses related to the breakthrough would affect the balance sheet of Kawasaki. While upfront costs for materials, advanced manufacturing, and testing had risen, forecasted profitability benefited from premium pricing strategies and increased volume. That engine and suspension package would command a price premium justified by performance gains and exclusivity. Leasing and financing options adapted to reflect the high value proposition. Investors saw the potential for sustained revenue growth not only from initial sales, but also from software updates and service packages. The event catalyzed a re-evaluation of how value is created and captured in the motorcycle industry. Even as the applause from the stage began to fade, conversations among engineers, designers, and executives shifted to the road ahead. Kawasaki's unveiling had laid bare not only a revolutionary engine and shock assembly, but a vision of motorcycling's next chapter. Industry insiders recognized that the implications extended far beyond raw performance. At the heart of the announcement was a modular architecture so flexible that it could underpin a range of models from sport bikes and street fighters to adventure tourers and even off-road machines. Development studios immediately began sketching platform variants featuring different states of tune, wheelbases, and frame geometries, all leveraging the same core powertrain. This would dramatically shorten product cycles and reduce development costs, enabling Kawasaki to respond swiftly to emerging trends and regional preferences. Competitors, too, were forced to reconsider monolithic model architectures in favor of more nimble, scalable systems that could accommodate a spectrum of rider demands with minimal re-engineering. In effect, Kawasaki had introduced not just a new engine, but a blueprint for future-proof production planning. The energy unleashed by the showcase extended into virtual realms as well. Digital twins of the new powertrain and suspension suite became a focal point of Kawasaki's engineering roadmap. By integrating high-fidelity simulations with machine learning algorithms, the company planned to iterate control software far more rapidly than ever before. Virtual prototypes subjected to thousands of simulated hours of stress, thermal cycling, and dynamic loading would feed data back into design loops, enabling engineers to fine-tune performance parameters before the first metal part ever reached a dynamometer. This approach promised to cut months from testing schedules and reduce costs associated with physical prototypes. Soon after the unveiling, Kawasaki research centers erected dedicated simulation farms, bristling with GPU arrays and AI accelerators, aimed at refining every RPM curve and damping profile through automated data-driven processes. Rival brands, alarmed by this leap in digital capability, scrambled to bolster their own in-house simulation tools and forge partnerships with software firms specializing in predictive modeling. Meanwhile, Kawasaki's dealer network faced the challenge of translating these high-tech advances into compelling showroom experiences. Traditional dealership floor plans, rows of static machines under glass, no longer sufficed. To convey the full impact of the integrated engine and suspension system, Kawasaki authorized the rollout of immersive demonstration pods equipped with interactive kiosks, augmented reality headsets, and dynamic ride simulators. Prospective buyers could don AR glasses and see real-time overlays of coolant flow, suspension stroke, and combustion chamber dynamics as they virtually navigated winding mountain roads or high-speed tracks. The visceral sensation of throttle response, haptic feedback through the handlebars, and shifting weight distribution were replicated with astonishing fidelity, giving riders a preview of the synergy between rider and machine before ever mounting the saddle. This new retail strategy elevated the buying process into a multi-sensory event and set new standards for customer engagement. Across the industry, showrooms would need to invest heavily in experiential marketing to compete. Beyond the showroom, Kawasaki's customer experience team redesigned service protocols to match the precision of the new technology. Rather than generic oil changes and suspension rebuilds at fixed intervals, maintenance schedules became fully individualized, driven by telematics data transmitted from the motorcycle to cloud-based analytics platforms. Sensors embedded within the engine and shock assembly continuously monitored metrics such as lubricant viscosity, bearing clearances, and hydraulic damping performance. Service advisors received alerts pinpointing potential issues days or weeks before riders noticed any change in behavior. Workshops transformed into high-tech centers with diagnostic consoles displaying 3D component models, cross-sectional thermal maps, and predictive lifecycle curves. Technicians, armed with tablets and guided by AI algorithms, could perform targeted interventions, replacing only worn parts or adjusting parameters, rather than undertaking wholesale component swaps. This shift from reactive to proactive service promised to reduce downtime and build customer loyalty, while also showcasing the benefits of integrated hardware-software ecosystems. The new engine's adaptability extended into Kawasaki's electrification strategy as well. Although the unveiled unit was fully internal combustion, its modular design inspired thoughts of hybridization and eventually, full electrification. Researchers noted that the compact high-efficiency cylinder block could serve as a generator in a range extender setup for longer-range electric motorcycles. By integrating a compact electric motor into the crankcase or output shaft, Kawasaki engineers envisioned hybrid sport tourers capable of silent urban travel and roar-down boulevard bursts with a twist of the throttle. Battery packs could be sized to conform to the bike's trellis frame, preserving mass centralization and handling dynamics. Early feasibility studies in Kawasaki's California design studio explored software architectures that would manage seamless transitions between electric and combustion modes, all governed by the unified control network revealed alongside the engine. As global regulatory pressure intensified to reduce carbon emissions, this hybrid pathway offered Kawasaki a bridge between high-performance traditions and an all-electric future. Competitors recognized that the line between gasoline and electric platforms was blurring, and that breakthroughs like Kawasaki's would accelerate the convergence. On the track, the ramifications of the new platform rippled through every racing category. Technical directors in MotoGP paddocks began analyzing how the dynamic valving of the suspension could be integrated into active aerodynamic setups, using real-time lean and yaw data to adjust winglets and diffusers. Endurance racing teams speculated on extending service intervals by leveraging improved thermal management, potentially reducing pit stop durations. Production-based series looked forward to homologation specials straight off the Kawasaki production line, enabling privateer outfits to race machines with unprecedented factory support. The ease of recalibrating engine maps for different fuel grades and altitudes promised performance consistency across global circuits, leveling the playing field for teams traveling from Sepang to Silverstone. In parallel, Electric Superbike Series organizers reached out to Kawasaki for collaboration on hybrid demonstration races, seeing in the new engine architecture a template for gradually integrating battery electric elements into championship rules. In a sport defined by millisecond margins, Kawasaki had handed the grid a new set of variables to optimize. Manufacturers of complementary technologies were quick to line up partnerships. Brake system innovators developed new caliper designs accommodating higher cornering loads enabled by the advanced suspension. Tire companies engineered rubber compounds with bespoke carcass constructions matched to the engine's torque delivery profile, balancing grip and longevity. Helmet and protective gear firms integrated heads-up display modules that interface with the bike's sensor networks, projecting shift lights, lean angle warnings, and navigation cues into the rider's field of vision. Even apparel brands explored smart textiles to measure rider posture and communicate adjustments via haptic feedback. This blossoming of ecosystem collaborations underscored how one breakthrough component could catalyze a cascade of innovation across the entire motorcycling infrastructure. Concurrently, Kawasaki's intellectual property portfolio swelled with new filings covering combustion chamber geometries, ceramic composite formulations, adaptive damping algorithms, and integrated control protocols. Legal teams around the world prepared for potential litigation as competitors challenged patent validity or pressed for licensing agreements. At the same time, Kawasaki pursued cross-licensing deals with academic spin-offs and research labs specializing in advanced materials and sensor fusion. The company opened select aspects of its engine control software under limited open terms, inviting third-party developers to create performance modes and rider assistance features. This measured openness aimed to spur community engagement and accelerate feature development while safeguarding core proprietary algorithms. The resulting tension between collaboration and protection would define Kawasaki's strategic posture in the intellectual property arena. In government circles, transportation regulators and road safety authorities took note of Kawasaki's leap forward. The ability to dynamically adapt suspension stiffness and engine output based on real-time data raised questions about standard testing protocols and type approval processes. Some jurisdictions began drafting new certification guidelines for adaptive systems, requiring demonstration of fail-safe modes that would revert machines to predictable behavior in case of sensor or software faults. Insurance regulators, intrigued by the safety potential of advanced rider assist features, contemplated incentives for riders choosing models equipped with Kawasaki's integrated control suite. Should a bike autonomously reduce power during perilous lean conditions or activate emergency suspension settings when a sudden obstacle is detected, insurers might offer premium discounts. Kawasaki's breakthrough thus catalyzed discussion of regulatory evolution, accelerating dialogue on the role of electronics in enhancing rider safety. Educational institutions responded in kind. Technical universities in Japan, Germany, and the United States announced new courses devoted to holistic vehicle systems engineering, drawing inspiration from Kawasaki's model. Programs bridged mechanical, electrical, and software engineering disciplines, integrating modules on combustion dynamics, sensor network design, and human-machine interaction. Kawasaki-sponsored scholarships attracted top talent, while research collaborations furnished students with access to real-time data streams from prototype engines and simulation rigs. The next generation of engineers thus learned to think in terms of integrated platforms rather than discrete subsystems, shaping a workforce ready to push boundaries even further. In parallel, vocational schools updated curricula for motorcycle mechanics, emphasizing diagnostic software, embedded systems calibration, and predictive maintenance techniques. For aftermarket tuning businesses, Kawasaki's announcement spelled both threat and opportunity. The increased reliance on sensor-driven controls and proprietary software meant that traditional plug-and-play performance parts risked voiding warranties or causing system conflicts. Yet visionary boutique shops saw a new frontier in custom software maps, bespoke suspension profiles, and encrypted firmware modules that could be tailored to individual riding styles. These specialists would need to invest in secure coding practices, reverse engineering tools, and partnerships with independent software vendors. Meanwhile, accessory manufacturers envisioned bolt-in hardware interface kits enabling data logging, connected ride coaching, and even live streaming of performance metrics to social platforms. The aftermarket landscape would shift from purely mechanical enhancements to a blend of hardware and software services. As Kawasaki prepared to ramp up production, the company turned its attention to supply chain resilience. The novel ceramic composites and specialized polymers integral to the engine's performance depended on a handful of suppliers with limited capacity. Kawasaki invested in dual sourcing agreements and capacity expansion projects, including identifying alternate feedstocks and exploring circular economy initiatives to recycle ceramic waste back into manufacturing. Logistics teams optimized inventory buffering strategies and contingency plans for geopolitical disruptions. The COVID-era supply chain upheavals had underscored the fragility of global manufacturing networks, and Kawasaki's leadership was determined not to repeat past mistakes. Their robust planning would serve as a template for industrial partners across the sector. Meanwhile, the marketing narrative evolved beyond horsepower and lap times to encompass the emotional bond between rider and technology. Kawasaki's brand team crafted stories around the idea of machine as partner, highlighting how the bike's adaptive systems learned from rider inputs to create a symbiotic relationship on every journey. Campaigns featured documentaries following test riders breaking personal records, aided by the bike's ability to anticipate lean angles and throttle demands. Social media activations encouraged owners to share data-driven ride logs, mapping their routes alongside performance heat maps generated by the engine's onboard analytics. This focus on community and co-creation fostered loyalty and positioned Kawasaki not merely as a manufacturer, but as a facilitator of personal achievement. Looking further ahead, Kawasaki's engineering think tanks initiated blue sky projects to extend the principles of integrated combustion and suspension into other mobility domains. Concepts for marine outboard engines borrowed the ceramic composite liners and active damping technologies to deliver smoother power delivery in choppy waters. All-terrain vehicle prototypes leveraged the same adaptive suspension algorithms to enhance traction on loose surfaces. Even light aircraft developers expressed interest in applying Kawasaki's thermal management breakthroughs to small piston engines, aiming to improve fuel efficiency and lower emissions for recreational aviation. The cross-pollination of ideas between motorcycle design and adjacent industries underscored the transformative potential of that initial announcement. In boardrooms around the world, corporate strategists studied Kawasaki's bold move as a case study in innovation leadership. They debated the optimal balance between proprietary control and open collaboration, between hardware precision and software flexibility. Some warned of the risks inherent in tightly integrated systems, higher upfront costs, potential for software bugs, and the challenge of servicing in remote markets. Others pointed to the clear advantages: faster time to market, stronger brand differentiation, and the ability to command premium pricing. What emerged was a consensus that future winners in the mobility space would be those who mastered the art of holistic engineering, delivering seamless experiences rather than isolated component benefits. Kawasaki had signaled the way forward, and the rest of the industry would either follow or cede ground. Against this backdrop, Kawasaki's internal culture underwent its own transformation. Teams once siloed into engine, chassis, and electronics departments found themselves working in cross-functional pods dedicated to specific market segments. Daily stand-ups featured mechanical engineers discussing software calibration, software architects brainstorming material science challenges, and designers considering thermal flow alongside aesthetic lines. Management reshuffled reporting structures to empower these pods with end-to-end responsibility, accelerating decision-making and fostering a sense of collective ownership. The shift not only sped up development cycles but also energized employees, who saw firsthand how their work contributed to groundbreaking machines. This cultural evolution mirrored Kawasaki's technical breakthrough, proving that true innovation required both technological prowess and organizational agility. In the wake of the industry shockwave, Kawasaki's competitors unveiled their own responses. Some released preview sketches of engines with revised valve train architectures and carbon fiber suspension components. Others announced partnerships with software firms to enhance ride-by-wire systems and expand electronic rider aids. Yet many fell short of Kawasaki's level of integration, offering incremental improvements rather than systemic leaps. Analysts noted that while it was easy to announce partnerships and concept sketches, matching the depth of Kawasaki's engineering investment would require years of sustained focus and capital. The early movers among Kawasaki's rivals found that the bar had been raised not just for performance, but for the very definition of what a motorcycle could be. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on Kawasaki's new engine? What impact will it have next? We want to hear from you. Thank you for watching, and see you next time.